So welcome back to the class again. Let's go forward. So let's take it forward from where we left on Friday. So we're looking at stochastic population dynamics. And so we started looking at an equation of this form in general, a population dynamical equation of this form. If we define x as the perturbation from the equilibrium, we showed that under linear approximation, it followed the following. Following dynamical equation, right? The perturbation follows this simple dynamical equation. And then this is a very, very well studied and important process known as Ornstein-Uhlenbeck process in the stochastic process literature. It's a very prominent process, both from the point of view of physics and mathematics, because it really describes what happens near equilibrium. That's the sort of broad motivation. And on its own, it's a convenient stochastic process where one can derive a whole bunch of mathematical properties, right? Okay, and then this is the mathematician's version of writing the same. Okay, where mathematicians do not write stochastic differential equations in the complete derivative form. They write in the form of increments. Okay, but they are equivalent. They have same properties naturally. Okay, so and we learned a few properties of this model. One is that the mean of the stochastic variable x is basically given by this, right? The initial value which decays exponentially. Okay, so the mean basically follows the same pattern that we expect in the deterministic systems. We also looked at variance. If I remember correctly, sorry, I don't have, just trying to get better space for myself when I write. Okay. It has these following properties: sigma squared by 2 alpha 1 minus e power minus 2 alpha t. Is that right? This is what we found from the last class. Okay. Okay, excellent. That's right. And then we also found the correlation between xt and xt prime, and that was basically e power minus alpha t minus t prime. Okay, approximately it follows this, meaning the correlation basically decays exponentially. Okay, we had these three really useful and simple properties. Okay, that's the Ornstein-Uhlenbeck process properties. Okay, and especially the last equation, the correlation equation, lends itself to applications. Now, how do we now make connections between real data and this model? Okay. So for example, if you have a time series of the state variable or the perturbation from the state variable with time, and then it follows some trajectory with lots of stochasticity, one of the first things you would do is to compute this, the correlation function. It's also called autocorrelation because we're finding correlation between the same variable x and x, right? The same variable, but at different time location. This is called autocorrelation function, ACF in short. It's one of the first things you also learn in any time series, even in any sort of time series models that you learn in statistics. And this autocorrelation function, ACF, as a function of tau, in a process like Untitled process, is expected to decay exponentially. So what you do is compute this and then fit the data to an exponential, and then from that you must be able to estimate what is alpha. Okay. Fit exponential function to ACF and find alpha. Okay. And of course, if it doesn't decay exponentially, that means that there is something more than Untitled process that is happening in real data. Okay, so that's the summary of what we know about perturbations near equilibrium. Okay, and then we went a step ahead. We sort of thought of an application. Application to what we call, abrupt transitions. It's also referred to as regime shifts. People also call them tipping points. Okay, now this is a very interesting application in the sense that for the following reasons. One of the very early papers on the possibility of abrupt transitions in ecology was done in around 1975. Okay, probably much earlier. Of course, I think mathematical possibility may have been known at least a decade earlier, if not much earlier. Okay. So at least concretely, if you go back to theoretical ecology papers, you will find that by 1975 these ideas were clearly there. Something like harvesting model, for example, was was published by 1975. And 1977, Robert May wrote that review article on thresholds and dynamic in ecological systems. That I think I had asked you to read in the previous semester, right? And then we have the OU process. Okay, so this application required us to know about the thresholds, right? The idea of thresholds. And then the properties of OU process. And the properties of OU process, do you know when was that known? Probably. This was known, Arnstein and Uhlenberg. They were mathematicians or physicists. I don't know exactly, but they were from those fields. And there is, in fact, even a paper by the two of them that was at around late 1920s or maybe early 1930s. So these were known back in 1930s, the properties of OU process. And what you did in the Friday's assignment was the following, right? You made a bunch of assumptions to help us make links to the idea of regime shifts and and how can we even anticipate them. So there is an ecosystem where, let's say, population density is high, it suddenly collapses. Let us assume, for the sake of argument, that this is actually a perfect system where the model assumptions are valid. Okay, and the basic idea of application of OU process to thresholds, OU process and thresholds, both of them put together in the context of real abrupt transitions, was the following. So we take some window here, and then we assume two things. We assume that parameters of the model change very little in this time window. They do change, of course, but they do very little. Okay, and then we assume that it's a stationary process. So in this window, because of one, we sort of, because it is changing so little, we assume that it's a stationary process. So what is the meaning of a stationary process? Any stochastic process with temporally stable properties. For example, the mean, variance, correlations, they don't change in this window. So we made these two assumptions, and therefore the perturbations, if this was the if this is the expected equilibrium in that window, the blue line, we said that the deviations from that, which is n of at any point of time n, and then this average that I have found in the window, we assume that this follows an equation of this time. That's what you all did. And then and therefore you said that okay, OU process is a reasonable approximation, assuming the deviations are not too large. And then you argued that if you calculate the autocorrelation function and variance, you calculate that for each window. Okay, assume for this is for each window, right? And then you now plot the trends of these ACF or the variance as a function of time. And then what you basically argue, what these quantities basically will increase even before T is reached. So you're really, for each window, you're assuming a stationary process, and you're assuming that the parameters are slowly changing, and the combination of the two and our knowledge of thresholds and OU process, all of that put together, we arrived at these conclusions. Of course, the key point here is that alpha goes to 0 as threshold is reached. Again, it's something we had learned in the previous semester, and something now. As we approach bifurcation points, the return time becomes infinitely large, or the return rate becomes 0. Okay, so you put these two together to arrive at this conclusion, right? Now let me tell you what is interesting. So we knew these ideas of thresholds in ecological systems by 1970s, right? We knew these ideas of OU process much earlier. Do you know when were these ideas put into actual practice? You may not know. Let me just tell you, much of this ideas actually happened in 2000s. Okay, 2000, you can say 2000 to 2010 were roughly where many of the theory papers on these ideas came up, and the empirical evidence for this came between 2010 and you can say ongoing. When we say empirical evidence, how do you really make use of them? Because real data, of course, these assumptions are going to be tossed out, right? In some ways, they are never going to be perfectly valid. Therefore, there will be limitations in being able to apply these. Okay. But nevertheless, so these were called early warning signals. Or we can say early warning signals of thresholds or tipping points. Okay. So this is sort of one interesting application of fairly simple processes, fairly simple dynamical system understanding together with stochastic processes, how stochasticity influences real systems. Okay. Any questions?
So
okay. Yeah, go ahead. Yes.
So are there certain properties of the system that make them follow, say, OU processes, or are they generally applicable to like complex systems like animal population.
So let me clarify your question a bit. Are there certain properties that make OU process applicable? When I say what, certain properties of what?
Of the system.
Of the real ecosystems.
Yeah.
Yeah, it's a tough question. So, I mean, we do know that if you want to apply this, right, to any system, whether it's biological, physical, or whatever, right, you do need that the very first stage, they basically follow an equation of this type, right? If any real system follows an equation of this type, and if the fluctuations are happening around the equilibrium and not far from the equilibrium, then the OU process is a reasonable description. Does it answer your question?
Yeah.
So basically, you need to have something like an equilibrium, and of course, you don't really have a true equilibrium in any real system, but what you have is fluctuations around the equilibrium. Okay, so as long as the system can be approximated as fluctuating around the equilibrium, one can apply OU process, at least for some periods of time. And of course, now here is the thing: why was it? Although all the tools were available, why do you think it took so long for people to combine these ideas? If you were to speculate some reasons, why do you think so? To arrive at this, to apply to these, the ideas of regime shifts and tipping points, why did it take so long? I mean, it's always a useful thing to think about in general, especially when certain theory ideas are applied in biological contexts. Okay. There are two possibilities. You are applying to such a novel biological phenomenon that you have to actually develop a new theory. Okay. Alternatively, there was a time lag between theory and empirical validation and empirical application. Okay. If you again just go back to the other example we studied in the class, right? That of Turing patterns. So Turing proposed his ideas in 1950s, right? It's only actually in the decade of 2000s, early 2000s to late, that people even began creating Turing-like patterns in chemical systems. Okay, and their applications in the context that Turing himself developed, that took even longer. I think maybe that was possible only in the last decade or so. People, in fact, probably dismissed the idea because diffusivity of two components are not going to be different in most real systems because they are on the same media. Okay, so because the crucial criterion there was a diffusivity had to be different, and therefore people, although they write that there was a lot of appreciation from a mathematical point of view, the biological application took much longer, right? So likewise here, what do you think, if you were to speculate, what makes how long does it take to apply known theoretical ideas in the context of real systems? It's actually a useful question to think. Maybe you are working on a biological problem for which all the methods are there, we just don't know they exist. That's one possible reason, right? It's worth thinking, why do you think sometimes these ideas take so long? And I think some of the reasons in this case may have been the fact that people really viewed this as a, people never, first and foremost, sometimes it's a question of right timing. Okay, people actually put these ideas together to create new ideas. It often is a question of timing, and often it's also a question of data. People are driven by, can I understand something about data, right? can understand. And these type of data sets sort of were becoming available only by 2000s, decade-long data sets. For example, in lake ecosystems, people had begun measuring phosphorus content on by mid 2000s on a daily basis, and with new sensors and all coming up, people now began to have really high quality time series, which was not possible beforehand, before let's say if you were to ask in 1970s. Okay. And one is that of availability of data sometimes drives the questions. Sometimes uh, it just takes time for people to combine already known ideas to make a new idea. And sometimes it's very, at the end of the day, it's also science is human enterprise, right? So that's and driven by sociology of who does what. Okay. So in that sense, again, this took a lot of time. Those were the possible reasons one can think of why there was such a gap of applying these two combinations, with some assumptions, of course, to sort of ask the question, how can we convert these theoretical ideas to actually in a useful way, in a measurable way? Okay, any questions before I go forward? Okay, so let me now introduce one more concept that sort of extends this, and it will become useful for our future classes. Okay, so I will in the assignment, I will give you some papers sort of on both empirical aspects of this, okay, and also some theory and some empirical aspects of this. Okay, the next assignment. Okay, so another idea that's actually useful in this concept is that of effective potentials. Again, I believe I covered some of it in the last semester, but let me just do it again. Okay, so we have an equation of this type, right? Population dynamics is given by this growth function f of n. So let us define a function u of n, which is basically integral of f of n dn from some n0 to n. So this is purely a mathematical construct. So f is the growth function. I'm integrating this and then creating a new function u of n. So this u of n has an interesting property. So to see that, how do we do that? Okay. If you want to invert this, what do you get? Let's take du by dn on the left hand side. Take the derivative. So what is the derivative of this? This will be minus f of n. Okay. So these two are basically equivalent. This is in the integral form. This is the differential form. Okay. Now let us. In other words, what I have really done is I have written down this n dot, which is equal to f of n, in the form of this some function where this is true. Okay. So now let us look at this quantity du by dt. What is du by dt? Du by dt can be rewritten in the following way: du by dn times dn by dt. So basically I have multiply and divide by d of n here. Okay, and then loosely speaking, okay, now what is du by dn? Du by dn is minus dn by dt. So the first term is nothing but minus dn by dt. The second term remains dn by dt. Don't change anything about it. So now if you put these two together, complete the multiplication, you have this. So what this shows is that du by dt is equal to minus n dot square. What is, so n dot is some value, right? It can be, it's a rate of change of population size. N dot can be positive, it can be negative. But n dot square is always positive. And when you multiply a positive number with a minus sign, what you get? You get a negative sign. Therefore, so this function, this right-hand side is always less than or equal to 0. That means that du by dt is always less than or equal to 0. So what does this? So what does it mean when a function is, when a rate function, du by dt is a rate function, right? What does it mean when the rate function is always less than non-zero? That means that u is always decreasing. Time, of course. Does everyone accept this interpretation? Okay, so let me just repeat what we have done. Now, this is the population equation, population growth equation. I have basically rewritten, I have just written the same equation in terms of u now. N dot is du by dn, and it's entirely, because f is a nice smooth function, it can be written as derivative of another function. That's the basic idea. Once I do that, what I have shown is that this function u is always decreasing with time. Of course, the more accurate statement is it's non-increasing, because it can hit 0. That means it can become non-decrease. So basically it's non-increasing. It either stays same or it's always decreasing. Okay, that's the property of u. What does that mean is, we know that what happens to this equation, right? So when any system follows this equation, what happens to this system? This system basically goes towards fixed points, right? And flows to fixed points. In fact, stable fixed points. By the way, stable fixed points are same as equilibrium. So let me just do the same terminology. Flows to stable equilibrium. So n basically is going towards stable equilibrium. What is this telling? U is always decreasing with time. Can we make some connection between the two? Okay, so if you were to now, let's do the following. If you were to, on the x-axis, let us say we have n, on the y-axis we have u. Let us say that u looks like this, hypothetically. Okay, and as you know, population following the n dot is equal to f of n equation, n will change with time. Let us say the current value of n is this. Let's say this is n0. At time t is equal to 0, n is here. Now n will change with time. Can you tell me whether the n will flow upwards this function or downwards this function?
Downwards, right?
Downwards. Why? Because du by dt is negative. So u will change, but u will always reduce. Therefore, it has to come like this, downwards. Now, can you tell me, as it is flowing downwards, can it actually climb up the hill? Can it go further like this? How long will it keep on reducing? Let us imagine that it has now come to the bottom. So the n is reducing with time. Okay, it has come to the bottom. What is the value of u here? Let's say it's the minimum possible value of u here. Okay, in this entire function. Now, will the system move towards left further? What happens if it moves further? What happens to u? You will increase, right? Then that will violate this equation, right? So therefore, a system will keep flowing, and how long will it flow? How much will it flow until it hits the bottom of this, of the function u versus n? On the other hand, imagine I started the system somewhere here. What will happen now? Will it go this way? Will it go this way? It has to go this way because that's the direction in which u is reducing. Okay. Therefore, this function u is interesting and useful because you can think of population dynamics as a ball rolling in a landscape. Okay. Again, this concept was discussed and was there in the paper by Martin Scheffer et al., right? Which I had asked you to read in the last semester. Except that they did not really show that it was mathematically possible in that paper. Okay, but it is indeed possible. So basically, you can think of population dynamics of the system that follows this equation as a ball rolling in the landscape. Okay. Now imagine. Now let's go further. Let's ask. Let us actually now apply this idea. Apply this idea to OU process. What is OU process? X dot is equal to minus alpha x plus eta t. Okay, so what is the potential for this system? This is a noise term. Let us ignore the noise term. So potential for this is, as I have described, it's the minus integral f of y dy from some x0 to x. Okay. Now, what is f of y in this case? That is basically minus of alpha y times dy. I'll take x0 to be 0. It could be any arbitrary value. And let's do it from 0 to x. So what will this be? And if you do the integration, you will get that u of x is nothing but alpha x squared by 2. So the potential function, this is called potential function or also the landscape function for the OU process is basically alpha x squared by 2. So how does the plot of this look like? U. So it is 0 at x equal to 0 and then it goes up both the sides like a parabola. Okay, so where is the minima of this parabola? That's exactly at 0, which is also the stable equilibrium. Okay, so basically what this means is that in this case, and in fact it's a very general property, that the minima of the u of u also corresponds to stable equilibrium. Okay, and now let us go back to the full OU process with the noise term. So now I told you that we can think of this as ball rolling in a landscape. Now if there was no stochasticity, it would just flow down and sit here, right? But what happened? What do you think will now happen with stochasticity? Let's say this is the current location. What will happen with stochasticity? It can get kicked in various directions, right? So what the ball will keep doing is it now basically is truly a ball in a some kind of a cup where it's trying to come down to the bottom, but the stochastic processes are pushing it all around it. You should think of a vibrating sort of a a shaking cup, and the ball is therefore basically jiggling around at the bottom, right? It comes down because deterministic forces, but stochastic processes just push you out a bit. Okay, so you can basically think of stochastic population model near equilibrium, right? Stochastic population near equilibrium can be thought of as ball stochastically rolling in a cup or a sort of a landscape with a minima. Okay, Is everyone with me so far? Okay. So now let's go further and apply this to not just OU process, but to threshold dynamics. Okay, potential landscapes. And thresholds. Okay, let us say again we have a model like this. So let's do the following. I will actually introduce now a sort of a toy model of, but the toy model actually, unfortunately, that has, sorry, did anyone have a question? So maybe I'll avoid the toy model because even the toy model has a, yeah, go ahead.
Yeah. So on the page 2, when you write the u versus n, like on like even earlier, there shouldn't so why will it exactly not cross you? So if n dot is not 0, then it can still go towards the left hand side, right?
So when is n dot 0? Let's look at this equation.
Right. When minus du by dn will be 0 then.
Yeah, exactly, right? Yeah.
Okay. So it will be sort of slow down around that time.
Yeah. So in this representation, it's useful to note that the equilibrium will be given by du by dn is equal to 0, right?
Okay, so those are the fixed
meaning
anyway.
they are the extrema of u. Okay. And you should be able to convince yourself that the minima indeed corresponds to f prime n star less than 0.
Right. Yeah, makes sense.
Yeah.
Thanks.
Yeah. Okay, so let's look at potential landscapes and the thresholds. Now I was wondering, is there a actually, yeah, it's possible. Okay. I was thinking it's not possible. There's something called a normal. Okay, now let's just remind ourselves a model like a logistic model, right? Minus h. So we know this has a bifurcation diagram like this, right? So it has a bifurcation diagram like this, right? And star. Now, but then, as you know, this model is too complex. It has this very crazy term, model function. So what we will now do is write down look at a simpler model that just captures this region. Okay, that just captures this region. Okay, now those are called normal forms. So this bifurcation is called saddle node bifurcation. So what I'm now going to describe is something called a normal form for saddle node bifurcation. Okay, so that's given by this simple, let's call it y dot is equal to r minus, let's c minus y square. Is that right? Will this give me? I think yes. Okay. Yeah, y is equal to c minus y square. So what are the equilibrium for this? What will be the equilibrium for this? The equilibrium for this will be c is equal to y square, where y star square. This implies that y star is equal to plus or minus square root of c. Okay. That means there are two roots, plus root c and minus root c, and that is valid only when c is greater than 0. What happens if c is less than 0? Are there any roots? No, right? Okay, let's just invert this to make it look exactly like what we have. Okay, let's write this as c plus y square. That means that c is equal to minus y star square, or y star is equal to minus c plus or minus square root of minus c. Of course, this will be real only if c is negative. Is that right? Okay, now let us plot the equilibrium y star with c. As I told you, after 0, there is really no equilibrium, only between, we have two equilibrium. One is minus root c, other one is plus root c, plus square root of minus c, the other one is minus square root of root c. It will look like this. Should try this out yourself. There are two roots. This corresponds to plus sign root plus square root of minus c. This will correspond to minus square root of minus c. Okay. Now let us look at the stability. Now we don't know stability, therefore I have written them both in a dotted way, and I will make whichever of the two as stable. I'll make them solid line. Okay. Now let's go to stability. For that, I take the right hand side, f of y, right? F prime of y. What is that? That's basically 2y. And if I look at f prime of y star, where y star is equal to, let's look at the top branch. This one, what is that? That's going to be 2 square root of minus c. And what is this? Is this a positive number? That's right, it's a positive number, right? Okay, yeah. Okay, it will still not look exactly what I wanted, but it's okay. I'm going to live with it now. Okay, so this is greater than 0. That means that the positive branch is unstable. Does everyone agree with me? This is unstable. What about the negative branch with a minus sign here? That would be stable. Okay, so if I were to, so just do it for yourself, and then therefore we can now write down both the branches. So this will be unstable. This will continue like this, whereas this will be a stable branch. Okay. What this means is that as you increase c, the system will be in this equilibrium. It will follow this, but the moment c increases beyond 0, the system is now just look at this part of the bifurcation diagram with this part. With inversion, it looks identical, right? Or in fact, yeah, that's right. Yeah. With inversion, they look identical. If I were to just swap the stable and unstable, they will look identical, right? So basically, if I were to imagine that this was the stable and it was unstable, it has basically same features. And the simple equation has that form. Okay. Now, why am I doing all this? I now want to plot the potentials for this. How do potential look like for this system? Okay, let's plot the potential. U of x. It is integral of f of y dy 0 to x. So what is that? Minus of c plus y square dy 0 to x. Okay, what would that be? Minus cx minus cy cube by 3. So basically potential looks like this. Sorry, it's x cube. Okay, so potential is minus cx minus cy cube by 3. Okay, I think I did not choose the right good form of this. It's a bit of mess. It's a bit messed up, but it's okay. I can't change now. I'll have to do all the calculations again. But anyway, the results will not really change. Let's now plot the potential function u. Now, I know that with minus sign, it's a bit hard to imagine what's happening. You are on the minus sign, and I know there are two roots, right? I know. Let's look at values of c being negative. In such a case, the entire thing is basically can be thought of as x minus x plus x cubed by. Okay, I have made a mistake, which is that's correct. Yeah, x plus x cubed by 3 with negative sign. So how will this look like now? So consider c negative, which is when we have two roots. How will this function look like? So actually, I don't see any, maybe did I make a mistake by the way in any of my calculations? Okay, I don't hear any answers.
It doesn't look like it.
Okay, so there are two roots. Let's say c was minus 4. Okay, we'll have two roots, one at 2, other one at minus 2, right? Okay, so the one will be at 2, other one is minus 2. Is that correct? If c was minus 4, I'm just putting some numbers to make sure we are fine. And because c is negative, so basically I think the pattern of this will look something like this. If it will look like this. Is that right? But it doesn't quite seem like I have problem, because for x very, very large and positive, because c is negative.
So won't there be three roots? Because x is equal to 0 is definitely one root, right?
X equal to root of what? Sorry, u is 0.
Root of, yeah, u
is
will be
0. It doesn't mean it's a root, no?
Sorry, I mean u will be 0 at x equals to.
Yeah, I mean I have to just shift my graph.
Yeah, okay.
But I think there is some mistake that I'm making, because c is negative, right? And when x is very, very large, it must go to infinity. It must go to infinity, no?
So
one with a negative sign.
Okay, c is also negative. Sorry, yeah. So
maybe that means it's actually, and when c is negative and x
starts
is
from the
minus
bottom, right?
when x minus infinity. So is this how it's going to look like?
Yeah. I think that makes sense. Yeah.
This makes sense, no? But somehow that means the positive branch is stable. I'm not getting that.
Oh yes, that is true.
Anyway, I mean, I encourage you to just find out, do the calculations, and check for yourself. It's clearly I have made some mistake somewhere. Okay, maybe some minus sign I have messed up. Okay, so caveat. I've just write the caveat. Some sign has been messed up. Okay, please check. But the point is the following: if basically when you have even a saddle node bifurcation like thing, you can think of ball rolling in this landscape. Okay, this is the equilibrium, right? Ball will get kicked around, and when it kicks around too much, it will cross this barrier. Okay. Okay, because I have gotten the sign wrong anyway, I'm going to sort of just say qualitatively what we expect to find. What we expect to find is that when you have, I would like you to plot the potential function for different C, okay, as you approach bifurcation. So you will basically find, the following feature. So when you are far from threshold, what's the value of alpha? Alpha is large, right? And when you get closer to threshold, what happens to alpha? Alpha becomes smaller and smaller. So what does that mean, by the way? So I'm writing 3 potential functions for different alpha values. Okay, let's look at the local curvature, right? What was the local curvature? I mean, I'm sort of, totally mixed. I have given up on the cubic term now for the time being. Okay, alpha x squared by 2, right? And alpha is reducing and getting closer to 0. Do you agree this is how the potential function will now look like as you get alpha closer to 0? Basically, the curvature at the bottom is reducing. What happens? How do you compare a ball rolling in this landscape versus this landscape? What do you think will be the impact on the fluctuations?
When alpha is small, the ball can roll out of the minimum value.
It can assume, assume that, it's sufficiently wide also. Don't worry about the width of it. Okay. Okay. So do you think it will fluctuate more in this case or in this case?
It will fluctuate more when alpha is small.
Right. As alpha goes to 0, right? Okay. So as alpha goes to 0, fluctuations increase, and that's precisely what we found make, what you all said about variance, right? Do all of you agree with that? When Friday assignment, you all said that the variance will increase, and you did that by looking at the formula for the variance term, which was this. Formula for the variance was this, and then you looking at that, you said that as alpha goes to 0, the variance will increase. We arrive at this. We are now arriving at the same conclusion by more of an intuitive picture. As alpha reduces, the sort of this potential well becomes shallower and shallower. Okay, and when you kick a ball in a shallow landscape randomly, it is prone to more fluctuations in a shallow landscape as against a deep landscape. This we call this deep. This we can call shallow. Okay, I will leave it as an exercise for you to think how to explain increased correlations. Can you use this landscape picture to argue how to explain increased correlations? That we were able to argue by this formula, right? As alpha goes to 0, e power minus alpha, a term will increase. But can you arrive at the same conclusion by looking at this intuitive picture? Okay, so I'll leave it as an exercise. Okay, and then if I had gotten all the signs and everything right, you would have found one more feature of the landscape, by the way. If you observe the landscape, what would have happened if I had not gotten things right? What you find is that as you approach the threshold or bifurcation point, you will find that this potential is symmetric for alpha large. It becomes more and more asymmetric when this potential landscape is, this landscape becomes more and more asymmetric when alpha becomes small. What do you think it will have impact on fluctuations again? As you go from large alpha to small alpha.
Does the asymmetry have like a direction?
Yeah, clearly it has a direction towards the other state. If the asymmetry is changing bit with time, then it becomes symmetric effectively, right? So there is a directionality here.
The sort of the fluctuations will push the system towards the other stable state in some
Yeah,
ways?
that's absolutely right. Yes, but let's say it hasn't yet gone there.
But like, oh, okay. So, but some of, as in, for some cases, it will be in this state. Like, sort of, there should be sort of skewness in the levels in some ways.
Yeah. So basically, here, in the symmetric landscape, the fluctuations will be, sorry, it's a very horrible plot. Sorry, the fluctuations will be symmetric around the mean. Okay, whereas when you have an asymmetric landscape, fluctuations will get skewed like this. Okay, so absolutely. So what we will find is that you will get more and more skewed fluctuations as you approach bifurcations of thresholds. Okay, this is to show that why am I showing you all of this, as basically what I have tried to do is to introduce simple mathematical theories of how to analyze stochastic systems, and taking an example of how we can actually make some, see all of these, right? Just think about the following, right? Now if you were to summarize all of this, right, as real systems approach thresholds, you can actually observe some measurable quantities, right? Increase in variance of the time series data or the state variable, right? And you expect increase in correlations in data. And finally, you also expect increase in skewness or the asymmetric fluctuations. Now, what is interesting about all of this is that these are all actually, we used fairly simple mathematical frameworks to sort of make some testable, measurable predictions, right? So at the end of the day, you want your theory to be useful to real data, and we use theory for two reasons, and one is to sort of understand and get some qualitative insights, but we also want to be able to apply in some cases, and this is one example of how we can actually apply and make some inferences about what might be happening to system in a very dynamical way. So unlike the Turing patterns case, right? Turing patterns, what do? We have a model and it produces patterns, and we just check visually, oh, do they look same, right? That's one way to think about the way we think of Turing pattern application to real data, right? Of course, one can try to do a bit more, but it becomes a bit harder. And of course, one can see where the parameters sort of ranges and estimations, do they match with theory, right? Are the processes similar to what's happening in real data? But they're all sort of still at a qualitative level. But this is interesting in the following sense, although it is also increase is of course a qualitative measure, but it's increasing in a few specific quantities. We can actually, this is an example of how we can use theory and make some testable predictions about measurable quantities, and all of this is happening in what we can say in a dynamical context. Because the parameters here are changing over time, right? The alpha is changing, albeit slowly, but it is changing with time. So I find this as an interesting example. Of course, of course, there's also an example I can give you because I know very well about this and we work on these ideas in our lab. Therefore, I know very well, and I thought I can tell you this example more confidently, and it's something that I don't know very well about. So this is an example of how we can use these kind of mathematical tools in real ecosystems. So what I will do is, I'll ask you some questions about this, and also maybe giving some empirical papers. You can read up some empirical papers and how people have tried out these ideas in real systems. Okay, so I will stop here today. Let me know if you have any questions.